The second paper is called Mathematical Modeling and Motion Analysis of Conveying Object Moving on Rotating Shafts, and that will be presented by Professor Fumihiko Asano, who is here, I think.
Hi. Can you hear me?
Yes. Thank you.
Okay, I'm ready. Okay.
Yeah, go ahead, please. Yeah, thank you very much.
Okay. Can you see the slide? My slide?
Yes, we can see your presentation.
Okay. I'd like to start my presentation. Okay.
Yes. Go ahead. Thank you.
Okay. Thank you for your introduction. This is Fumihiko Asano from GIST Japan.
Yes.
Okay. The title is Mathematical Modeling and Motion Analysis of Conveying Object Moving on Rotating Shafts. Sorry, this paper was submitted as a short paper for poster presentation. So today I'd like to make a short presentation.
Thank you for that.
Toward novel technologies that contribute to factory automation, the author is now investigating the feasibility of the conveyor system illustrated in Figure 1a. A thick disc-shaped object moves on two inclined rotating shafts using the effect of gravity and frictional forces as the contact points. In the future, we hope to realize more advanced object transportation by applying vibration to the entire stage. This picture shows our prototype conveying machine. The two rotating shafts are made of the same material and have the same radius R1 and R2 and rotate at the same speed but in opposite directions. Modeling. In this paper, we consider a loupe-shaped conveying object illustrated in Figure 1b like this. It has a shape where a circular upper part and rod-shaped lower part are combined. Let R be the radius of the circular part and XY be the central position of it. We assume that its center of mass, COM, here, is located L meter below the two rotating shafts, R1 and R2, below the rotating shafts, and that the mass is m kilogram, and inertial moment around COM is I. It vibrates in the lateral plane according to the frictional force effect acting on the contact point with the two rotating shafts, here and here. There is also a height difference between the two shafts. There is also a height difference between the two shafts. This is adjusted by the angles phi1 and phi2. Let Q equal x, y, theta is the generalized coordinate vector. The equation of lateral motion and harmonic constraint condition become mq2 dot plus h equal j transpose lambda plus jv transpose lambda. And the harmonic constraint condition becomes jq dot equal 0. Where lambda is the constraint force vector acting on the central position of the circular part as shown in the next figure. Here, this is the constraint force vector lambda. The term J mu transpose lambda is the frictional force vector and can be determined by resolving and rearranging the constraint force vector. The conducting force vectors lambda 1 and lambda 2, can be obtained by these simple calculations like this. The frictional force term is then determined accordingly. By solving these simultaneous equations, we can derive the constraint force vector lambda like this. Okay. Next, the model of dynamics of sagittal motion. On the other hand, as illustrated in this figure 1D, the equation of sagittal motion is simply modeled as mg2 dot equal mg sine phi 3 minus mu 3 lambda y, where phi 3 is the slope angle, like this. And we consider to use this smoothing function, not using sine function, but using hyperbolic tangent to avoid chattering around z dot equal 0. It is assumed that the motions in the lateral motion and sagittal motion, it is assumed that the motions in the lateral and sagittal planes don't interfere with each other. Motion analysis. Figure 2 shows the simulation results of the object motion that moves on an inclined rotating shaft. Theta dot, and z dot, respectively. We can see that the object moves forward at a constant sliding speed while vibrating laterally. So it vibrates. It draws a sinusoidal curve in the lateral motion, and the moving speed converges to a constant value. Motion analysis. These figures, the analysis results of the moving speed with respect to effect of omega 1, the shaft rotating speed, and effect of mu 3 0, the frictional coefficient, and phi 3, the slope angle of the shaft. From figure 3a, we can see that the conveying speed is quickly saturated with an increase of omega 1 or decrease of omega 1. However, this is different from the experimental results, unfortunately. So finally, I'd like to show you the experimental movie. It was clarified that the moving speed motorically increases with the increase of the shaft rotating speed. There is a significant gap between the simulation and the experimental results. Then we have to reconsider the mathematical modeling for the motion in the sagittal plane. So unlike the simulation results, the moving speed monotonically increases with the increase of rotating speed. So we have to reconsider the mathematical modeling again. The conclusion and future work. A novel conveying system with two rotating shafts using actual friction effects has been proposed. Mathematical modeling, basic motion analysis, and experiments have been conducted. However, there is a significant gap between the simulation results and the experimental results. The dynamics of the sagittal motion must be reconsidered. Now we are attempting to develop the new mathematical model based on the experimental results obtained. The detailed results will be reported in a future paper. That's all. Thank you very much for your attention.
Okay, thank you very much, Professor Asano. I will invite questions.